The nice thing about the forces unit is that the questions are going to follow a similar pattern over and over again. What you need to be able to do is analyze the information and follow the same pattern. So with this question here, which I'll give you a minute to copy down into your notes, it says, while bike riding down the street, you pedal with 950 newtons of force but experience a frictional force of 225 newtons. How far will the bike travel in 5 seconds? So the first thing we're going to do in this case is we're going to draw a free body diagram. Okay? We're going to draw a simple box, and we're going to say here the mass is 100. So right now, we don't have to worry about numbers. We just need to label the things that are going to be affecting this. Because we're on Earth, we're going to be having a force due to gravity. Now, because we're not accelerating through the ground, what we're going to be also experiencing is a normal force. Now, a normal force is kind of a tricky conceptual idea, but basically what happens is if you're on a surface, you're not accelerating through the surface. So therefore, there has to be some sort of force that's counteracting gravity. In this particular case, it's the ground. And that's what a normal force is. It counteracts the motion so that an acceleration isn't occurring. Now, if we're bike riding, we didn't say what direction we were going in, so we're going to arbitrarily say that we're moving this way, which means my force applied, which is the bike pedals, is to the right. Therefore, what we're going to have is we have to have our force friction opposing motion, because that, by definition, is what friction does. It opposes motion. So we've now got our free body diagram. Now we're going to put numbers on it, and we're going to put numbers on it here in this T-chart. Okay, so in the vertical, we've got our force gravity, and we've got our force normal. Now with force gravity, we know according to Newton's second law that force is equal to mass times acceleration. So this becomes ma. Now we know the mass is 100 kilograms, and we know acceleration due to gravity is 9.8. Therefore, our answer here is 980 newtons. And what direction is that going to be? That's going to be down. So next thing we need to do is we need to figure out our force normal. Now, we don't know what our force normal is. Force normal is not one of those things we can directly calculate in the way that we just calculated gravity. What we can do is we can look at the idea of net force. A net force is looking at all the forces that occur within a plane. So in this particular case, our net force is equal to the two forces in the plane because there's two forces here. There's our force gravity, and there's got our force normal. Now, if you're bike riding along horizontally, what's your acceleration going to be vertically? Well, the answer is 0. You're neither accelerating into the sky or accelerating through the ground. So therefore, we know it's going to be 0. Now, force gravity is equal to 980 newtons down. We don't know what force normal is. But we could do the math and figure out that our force normal therefore has to be 980 newtons up. Because if it was any other number, our net force wouldn't equal 0. Now let's look at the horizontal side. On the horizontal side, we've got two forces. We've got our force applied. And our force applied, if we remember, is 950 newtons. On the other hand, we got our force friction. Now our force friction is equal to 225 newtons. Now what I forgot to write on here are the directions. So if we assume that our force applied is going to be to the right, our force friction therefore has to be to the left. Now yet again, our net force. The net force has to equal all the forces within the plane. We've got a force applied to the right, and we've got a force friction to the left. So in this particular case, if we try to add these numbers up, it won't work because they're both going in opposite directions. So what we need to do is we need to subtract them. So 950 minus 225. So therefore, when we do the math, we know the answer here is 725 newtons to the right. So what we've just done is we've done step 2 and we've done step 3. Okay, this parts here that are on the top, for both sides, we organized our information in the T-chart. Once we did that, we did what we did here in step 3, which is where we found the net force both horizontally and vertically. So our next step is going to be finding the acceleration. Now, we know according to Newton's second law that F net is always equal to mass times acceleration. We know the cyclist has a mass of 100 kilograms. We don't know the acceleration, but we just figured out the net force is equal to 725 newtons to the right. Therefore, if we plug it into this equation, we know that that's going to be equal to 725 is equal to 100a, which means my acceleration is going to be 7.25 meters per second squared to the right. So in this particular case, it's asking how far we traveled, not the acceleration. And this is where all the stuff from last week, the kinematics equations, comes into account. Okay, now we know the acceleration on the bike is 7.25. So we know the acceleration is 7.25 meters per second squared to the right. We know the time in this particular case is 5 seconds. We need to make an assumption here, and the assumption is if we're trying to race on a bike, that our V1 is going to be equal to 0. So our last question is how far do we go, and that's where our displacement comes in. There's only one equation that fits all these things, and that's d is equal to V1t plus 1/2 AT squared. We plug our numbers into here. So 0 plus 1/2, 7.25. And I didn't bother calculating the VIT because I know anything times 0 is going to be equal to 0. Which means that my displacement is equal to 90.6 meters to the right. So to review, when I got the question, what did I do? I drew a free body diagram and I labeled all the forces. From there, I took the information and I put it into a T-chart. From the T-chart, I figured out the net force was on my object horizontally and vertically. I determined the acceleration of my object. And from there, I determined whatever it was the question was asking for. And in this particular case, it was how far I went.